Um, Hi, my name's Garrett Porter. I'm the CI engine team lead here with the Michigan Tech Clean Snowmobile team, and we're going to be presenting our compression ignition design for this year's knowledge event. Um, my name, I already mentioned my name, but our faculty advisors are Dr. Jason Blau and Dr. Scott Mears. I'm going to give a quick outline of our presentation today. We're going to talk a little bit about our team organization, go into our chassis selection and engine selection, and then talk about our chassis simulation, our engine and after treatment simulations, our fuel economy simulation link that kind of links our two chassis and engine simulations for the fuel economy event, and then talk about our future plans and goals. A little bit about our team organization. We're a 30-member team that's led by our exec board, which consists of our president, an SI engine team lead, a CI engine team lead, which is myself, a chassis team lead, and then new for this year, we brought on an instrumentation team lead to deal with the electronics and the testing equipment involved with both snowmobiles. And then we have two business team members that deal with our finances and our MSRP. Some things that we've brought over from our internships and industry have been project timelines. At the beginning of each year, we sit down, we do a full timeline from start to competition of all of our major goals and minor goals to be able to meet those. And then also we do a task list and progress tracking form. So that's shown in figure 1. Basically each team member, when they go to work on a project, they can put in their name, the date that they're working on it, the time that they start working, and then they write down a little bit of the goals, what they plan to get done during their time. And at the end of the day, or at the end of their time, let's say they have to go to class, they put the time that they left, it records the hours that they worked on that project, and then they also take some notes on where they finished up so that if another team member comes along and wants to pick up on that project, they know right where to start and what work's been done and what needs to be completed. This really helps us keep on track, keep track of not only what each team member is doing, but also where we're putting all of our time into projects and which projects are getting team members to work on and which aren't. And then finally, we have weekly meetings just to sit down, make sure everybody's aware of our current progress, what we're working towards, and what needs to get done to meet our goals.
Hello everyone, my name is Christopher Spencer. I'm this year's chassis team lead. This year we got together and we talked about different foundations that we could build our CI sled off of, and we as a team decided on a 2020 Ski-Doo Scandic wide track for a few main reasons. One, the biggest reason is due to the heavy attributes of a diesel motor and engine management systems, that the front suspension designs to optimize flotation effects in deep snow. I think together we believe that this would be highly beneficial to the customer in a practical setting. It's a lot lighter on a foundational level compared to our old competition sled, having a lot more cast aluminum pieces than steel components, and also it has a wide variety of utility options for the rear of the tunnel on the snowmobile.
Going on to engine selection, our team decided this year to go with a Kohler KDW 1003 diesel engine. The parameters are listed there to the right. 1028cc 3-cylinder liquid cooled, naturally aspirated, indirect injection diesel motor. It's previously been used in the power sports industry in a UTV, and we found that it had some advantages compared to our previous engine of the KDW 993T, which was a military engine that's no longer in production. We found that the 1003 is a current production motor, has widely available parts and a wide knowledge base that we can tap into.
So here, as a team, we decided on using the program AimSim to simulate the chassis driveline of the snowmobile. In this slide, I'm going to talk about the few foundational pieces that we use throughout the competition for different testing purposes. One being the CVT, the continuously variable CVT system, and furthermore, the gearbox, the final drive axle with the drivers, and finally the track system. As shown in 5 and 6, 5 is specifically used for the fuel economy model, which Isaac will, another team member, will talk about later in the presentation. That will account for any elevation, distance, drag on the system. And the drag based off of velocity, that is a comprehensive drag force implemented into the system to account for a comprehensive drag force based, including driveline drag, frictional drag against the testing surfaces, and also windage at higher speeds. That I'll talk about furthermore on the next slide. So how we did that was we pulled the sled down a similar snowmobile trail to a hard pack snow with a strain gauge in line with the tow vehicle. And what we did was we towed the sled at constant state at different speeds and measured the force it took to tow the sled at that speed. In figure 5, it shows how much force it took to pull the sled. Using a curve of best fit, we determined that this would be an easy and simple way to be able to summation all of the drag forces acting on the vehicle while in motion and in operation with an operator sitting on the snowmobile. So that's an accurate representation of weight effects and frictional effects in the snowmobile during operation. The CVT torque ratio being another dynamic parameter within the model, we determined that because of the complexity of a CVT system and the vast array of options and tunability of a system like that, would be easiest to set up tachometers both on the primary and secondary clutch and measure the speed ratio of both clutches at constant state speed, and simply taking the inverse to get the torque ratio. And by doing that and creating the figure 6 as seen on the screen, we were able to basically create a lookup table based off of a demanded engine RPM. We created a overall torque ratio that we can use in the model throughout to provide a variable gear ratio that the CVT system can run. Obviously, the scatteredness of the dots on the figure is not optimal, but due to time constraints and simply because we had to adjust some settings on the portable data acquisition system that we had on the snowmobile, we just had to change some settings and some history syseffects on the data logging system. So we would definitely like to improve on that in the future.
Hi, my name is Isaac Tussey. I'm a chassis team member, and I'm going to be discussing today the fuel economy model we had for AIM-Sim. So from competition, we were given a velocity versus time profile and an elevation versus distance profile. So we imported these two components into MATLAB and were able to find the required torque throughout a whole entire time span that was required of the snowmobile to be able to go the distance. So what that means is that we were able to say basically drive the system with a known velocity and then limit it by what our capable torque was and also what our maximum RPM is. And then in figure 8, you can see that we had a drag related to track distance, this is from MATLAB, basically saying that when you're going up a hill, basically just doing your simple block diagrams, we're able to find what was the required torque that was either added or given back into the system from going up or down a hill, and also from accelerating and deaccelerating. From this, so with all these components, we had outputs of the required torque, the engine RPM, and then the velocity versus time. And then we're able to compare that back with the original velocity versus time profile that was given to us in competition rules to see if we fell within tolerances. In the acceleration model, we were able to simplify it, and instead of having a PID controller, we had an engine controller. And inside that, there was parameters that were your maximum torque per the RPM that your system was given. So we basically gave it to the system a cue that you start at idle, and then you go to maximum capable torque for the whole entire RPM range. So how we were then able to find an accurate representation of that was that we changed our drag based off of distance to a drag based off of acceleration. Another MATLAB code basically saying what is the torque required of the system to go a certain acceleration. So that was then limited by what our physical motor was capable of. Our drag based off velocity is still the same with air resistance and everything else. So that is how we were able to find the outputs of the distance versus time, which is our 500 feet, and then our velocity. Thank you.
Hi, my name is Jacob Schallenbrand. I'm a CIT member, and I'm going to be going over some of our model overview for our engine simulation. So to accurately model our KDW 1003 engine, we chose to use GT Power, which is part of the GT-ISE software package. To obtain some of our initial inputs, such as the bore, stroke, valve diameters, and compression ratio, and a lot of other values, we actually use the Kohler Workshop Manual for the KDW 702, 1003, and 1404 engine family. All three of these engines exhibit identical engine geometry, aside from the fact that the 702 is only a 2-cylinder version. Our 1003 is a 3-cylinder, and the 1404 is a 4-cylinder model. Few other metrics that we needed, we actually measured by hand from a spare cylinder head that we have. We have a disassembled KDW 1003 engine down in our shop. Couple things that we took off that were like the intake and exhaust port sizing and the pre-chamber sizing that were needed for GT Power. For our camshaft profile, we actually measured that in lab. We went up to our running KDW 1003 at our dyno. We removed the valve cover and then fixed a dial indicator directly onto the cam lobe, and then rotated the engine through its 720 degrees of rotation and measured lift throughout it. We then adjusted the lift based off of the rocker length to find the actual lift and duration for the intake and exhaust valve itself. We also measured the lift and duration for the fuel lobe so that we could find the start of injection needed as an input for GT Power. So figure 11 displays the results from our cam profile testing with intake, exhaust, and fuel lift and duration. Figure 12 is an overview of our GT Power engine model only from intake port to exhaust port. I wanted to display this so that you can see the layout of our pre-chamber and pre-chamber connection. We ended up going with a pre-chamber injector to simulate our IDI injection. Some of the benefits of this injector is the fact that we had direct control of air-fuel ratio and delivery rate. So before we started using our engine simulation for emissions testing or to link it with the chassis simulation, we wanted to make sure it was as accurate as possible. To do so, we directly compared some of our simulation results to real-world results. The two metrics we chose for this were torque and cylinder pressure, mainly because these were two items that we had actual real-world data for. So figure 13 is a comparison for our torque values. The red line is results from running our engine up at our dyno, and the blue line is results from GT Power. This is a sweep done from around 1500 RPM to 3500 RPM. This test was also done at the same air-fuel ratio, since we have direct control of that with our injector. And while there was a little discrepancy, we were very pleased with how accurate our model was compared to our actual dyno results. So figure 14 goes over cylinder pressure. The red curve is measured and the blue curve is from GT Power, our simulated results. The red curve is actually from a 702 engine. This was from this was cylinder pressure data available to us from a test done for the United States Army up at the APS labs up here by the airport. Again, the curves are extremely similar in shape, which we were very pleased to see. And matching the cylinder pressure curve also proves that our combustion object within GT Power was extremely accurate. And even though the 702 motor lacks a cylinder with the same engine geometry and everything else being the same between the two motors, besides the number of cylinders, we felt that matching the curve between the two engines would be accurate enough for our simulation. So I also do want to note that both of these test runs within GT Power were done with our intake and exhaust on the motor, not just the model in on the previous slide from intake port to exhaust port. The intake and exhaust, Andrew's going to talk about in the next slide how those are developed.
So my name is Andrew Stahlheim. I'm CI team member and business team. So the first thing I'll talk about is our intake. Starting off with that, we started by scanning the intake and exhaust manifolds on our engine. So using the scan, we were able to bring that into Inventor, which I used, to create a solid model, which we then used to model a CFD simulation, which represented the flow characteristics of our engine at wide open throttle. So we were able to pull the flow data from GT Power as well as our dyno and just impart that on the intake side and measure the resistance between the inlet and the outlet of that manifold. To go with that, we used the senior design intake from the previous year on the Bearcat and also measured the resistance on that. Using the orifice plate within GEM 3D, we were able to simulate the resistance that was created across the manifold and the filter element, while we let GEM 3D basically handle the rest of the resistances automatically. Moving into the exhaust side of things, we used GEM 3D to create a 3D representation of our exhaust package, which was inclusive of the catalyst, the filter, and the muffler. The physical parameters we were able to measure from our current items that we have and are using on our sled. And going forward with that, the reactions within the catalyst and the filter, we both went to example models that we found within GT Power to create or to represent what we had, because it's a fairly in-depth process to model the actual active reactions within the catalyst. And what we found is that the results that we got out of GT Power matched what we had in the simulation fairly well. So we were fairly pleased with the results that came out of using those examples. So next, the sound portion of our simulation, we used the Yamaha Phaser muffler, which you saw modeled on the previous slide. So we took that and we implemented a microphone positioned according to J192 standards relative to the tailpipe out, which is in our case the end of the muffler. And we measured the sound pressure level according to those standards. Figure 18 shows the sound pressure level. The blue represents with all of our after treatment package on there, so the filter, catalyst, and muffler. And then the red represents a straight pipe configuration where we removed those items. We did this to just show a representation that our exhaust is in fact reducing the sound pressure coming out of our engine, as well as we had sample data from previous years using the straight pipe configuration, so we were able to verify that what we got out of the simulation is fairly close to what we're actually seeing out of the real engine. So overall, we reduced by approximately 86 dBA, which is fairly good. The overall was about 63 dBA for our after-treatment system, which we are fairly satisfied with.
Our fuel economy simulation link basically was built in order to connect our engine and chassis simulations for the fuel economy event. What it is a MATLAB script that takes in data from both AIMSIM and GT Power and is used to calculate fuel flow and tailpipe out emissions over that drive cycle. As I stated, the inputs for this simulation were the required torque and RPM that were talked about a little earlier from our AIMSIM chassis simulation, and then an engine AFR map shown there in figure 19 that was built in GT Power using the optimization tool, and several emissions output tables, one of which is shown in figure 20, built using GT Power, and finally an engine air to fuel or airflow versus RPM relationship that was built using GT Power data. And the outputs of this simulation, basically it takes all that in and we calculate fuel flow versus time and tailpipe out emissions in milligrams per kilometer based off of our required data and our data on how we understand the engine would be running. The team's future plans, on the CI side of things, we look to add electronic control to our KDW 1003 motor. We'd like to use our engine simulation to base that fuel control off of, so we have a reliable control. And then we'd like to tune it for reduced emissions while maintaining performance. Additionally, we'd like to add a turbo to our motor. We'd first like to implement it in our GT Power model and then use the simulation to guide turbo selection. And finally, the team is currently working on implementing the 1003 motor in our Scandic chassis. You can see there in figure 21 a scan of the Kohler motor that's being combined with scans of our Scandic chassis to create a reliable and safe design to place that motor within the chassis for future competitions. I just want to say thank you to all our sponsors and open it up to any questions.
Thanks, guys. I had a question on the noise aspect. When you say straight pipe, are you talking with the OEM's original muffler on there, or just right out, legitimately no sound dampening? What else we got? How did you guys overcome some of the challenges with this year and moving a lot of it into the simulations? Like, how did you identify the proper variables that you needed to measure to get the proper inputs so that your test results came to the conclusions you were hoping?
I guess I'm not sure. Jake, you can probably talk a little bit more on the GT Power side of things, and probably Chris or Isaac can talk a little more specifically on AIMSIM. But at the beginning of the year, from a team standpoint, we understood that we would have to be doing simulation, so we set out timelines to meet that. We knew that we would need basic engine parameters within GT Power, and then some of the ones that we weren't aware of, at least on the engine side. I know we went through the GT, now I can't, like, tutorials on that kind of walk you through what you would need to set up a basic engine simulation. So we had a fair idea of that on the engine side, and then on the chassis side, I know there's a pretty good layout of what would be needed in the competition guidelines. So we tried to meet those as close as possible. We understood that there would be losses in our system. We would have to model somehow, and we understood that there would be certain things like mechanical, like gear ratios in the gearbox, that we could just physically measure. I don't know if either the specific team members want to add to that, but from a team level, I remember that's what we were working on at the beginning of the year.
Yeah, at least on the engine simulation side, Garrett, you pretty much hit it right on the head. We knew pretty early on that we needed an accurate representation of our engine, simulation based somehow. After we chose to use GT Power, it was pretty much a matter of getting all the parameters that we need and then verifying the outputs so that we could use it for our chassis link.
Okay.
For the AIMSIM side, it was just very much that we knew we had inputs, we knew we needed outputs, and we had a few references from some tutorials, but besides that, it was basically trial and error. I could tell you 1,000 different ways we went wrong before we went right.
Perfect. And then lastly, we've got about 2 minutes here. When you guys are making your design decisions, how often did you consider like MSRP costs and the end product for, I guess, sales, if you want to call it that? Like, it's easy enough to say, oh, this engine is going to fit meet our requirements, but it's 3 times more than this other competition. Like, did you guys weigh those benefits and costs?
I'm going to assume, Andrew, you can probably answer this best being on business team.
Sure. It's understandable.
This is Hugh from Marla. Can I throw a question in really quickly?
Absolutely.
Yeah, just wanted to talk about the powertrain for a second and just ask a question about what assumptions you make. Port temperatures, intake temperatures, piston temperatures, that sort of thing. I mean, you again, you were a bit in the dark at this point in time. So, what did you do?
At least for intake temperatures for the GT Power model, I use the temperatures that were our dyno cell showed. GT Power measures all of like your piston temperatures, cylinder wall temperatures based off of like solvers within GT Power itself for the model. Since the only data we had for torque and power was from our dyno cell, our initial intake temperatures were matched for that air temperature and density.
Okay.
Also, to add to that really quick, for our model that was used with our fuel economy simulation, that would be outside, the air temperature and density were provided for us in the competition documents.
Okay. Thanks, guys. It's great.
Yeah, thank you. Good job.
All right.
All right.
All right.
Nice work, guys.
Good luck.
Thank you.
Gotta hop off to another one.